Okay, so we've looked at the properties of powers, properties of exponentials. We've looked at how we can simplify the quotient of two exponential terms. We've looked at how we can solve equations that involve variables in the exponent. And now what we're going to look at is the graphs of exponential functions. So the reason we're looking at exponential functions is because just like the properties of exponents are essential to understanding the properties of logarithms, right? We've definitely looked a lot at the properties of exponents now, and hopefully that will allow us, with some practice, to be able to understand better the properties of logarithms. Understanding exponential functions will also be essential to understanding logarithmic functions, because we're going to be studying the graphs of logarithmic functions as well. So let's start with a nice sort of simple example. We're going to be looking at the behavior of some exponential function y equals c to the power of x, where c is positive. Excluding one positive number, actually. We are going to exclude 1 as a possible base. And the reason for that is because the number 1 is actually quite a boring number for a base. More rigorously, we might say that the number 1 as a base doesn't exhibit the behavior that we define exponential functions to exhibit. Or in other words, it doesn't provide us with exponential growth or exponential decay. Okay, so we're looking at exponential functions only with positive bases excluding 1. Let's break this up into two possible cases. So for this first case, we're going to be looking at the graph of y equals c to the power of x for a base that is larger than 1. Okay, so a particular example that we might choose to do using concrete examples is usually useful in eventually understanding the more general language. So let's look at actually a specific example when c is equal to 2, when our base is 2. So we're looking at y equals 2 to the power of x. And we're going to look at the behavior of this function in general. So let's just do a traditional table of values here. Let's plug in a negative number, actually, as our first input. Again, what defines exponential functions is that their input, a part of what defines exponential functions is that their input, x, is in the exponent. This will give us different behavior than something like a polynomial function or a trigonometric function. It is unique to exponentials. Now, if we plug negative 2 in, what will that give us as an output? Well, that will give us base 2 to the power of negative 2. We know how to interpret this. This would just be 1 over 2 to the positive 2, which is just 1 over 4. So if we were to graph this result on an x and y axis, we would say that when we plug in negative 1, 2, we only really get 1 over 4 as a result. So a pretty small number. That's roughly 1 over 4. Let's plug in negative 1. That'll just be 2 to the minus 1, which is really just 1 over 2 to the positive 1, which is just 1 over 2. So here, I'll just plug in at negative 1. We get positive 1/2. If we put in an input of 0, that's just 2 to the 0, which is positive 1. So there's our next ordered pair plotted on our x and y coordinate grid. Let's plug 1 in. This is just 2 to the 1, which is 2. So when we plug 1 in as our input, we get 2 as our output. Let's plug 2 in as our input. That'll just give us 2 to the power of 2, which is 4. So when we plug 2 in, we get 4. And let's actually plug one more number in. Let's plug 3 in. That will just give us 2 to the power of 3, which is 8. So if we plug 3 in, we actually get, well, a number that is actually kind of off. Oh, it's off this graph. It's so high. So we can now just connect all of these points into a nice smooth curve. Exponential functions will always give us nice, smooth, continuous curves. And it will look something like this. And we can notice that it's actually growing quite fast. And it will continue to do that for forever. We can kind of have a gut check for this kind of growth. Let's say that we want to see what happens to this function if we plug in a super large number like 50. Well, that's just gonna give us 2 to the power of 50, which I don't know what that is, but I know that it's big. It's going to be a huge number. 2 times 2 times 2 times 2 times 2. If you do that 50 times, you're going to get an enormous number there. So we're going to have, let's just take the question mark out and replace it with huge. Right? This is going to give us a huge number. So exponential growth is definitely a surprising thing. Typically, as humans, we don't have good intuition for how fast exponential growth truly is. Even if we have something like 10 as our input, right? 10 isn't really that far on our x-axis here. Our x-axis is scaled similarly to our y-axis. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we plug 10 in for x, we'll get 2 to the 10, which is actually 1024, which is going to be way, let's do this at our input. This is going to be way higher than anything. We would need so many pages above this page to be able to graph how high that point would be off of our x-axis, right? So exponential growth is something that that is quite extreme. We can also notice that as we plug in smaller and smaller numbers, let's say we plug in, I don't know, negative, let's say we plug in -5, then that would just be 2 to the power of -5, which would just be 1 over 2 to the positive 5, which is really just 1 over 32, which is, that's a pretty tiny number. That's a pretty tiny number. It's, what I mean by that is that it's pretty close to 0, right? 1 over 32 is pretty close to 0. So if I go -1, -2, -3, -4, -5, I'm gonna have a point really, really close to the x-axis. And that kind of trend is just going to continue, right? If I have -50, that's just going to be 2 as my input. My output is just going to be 2 to the -50, 2 to the -50, which is 1 over 2 to the positive 50, which is incredibly tiny, right? This is an incredibly tiny number. What I mean by this is that it is incredibly close to 0. So we see that as we plug in larger and larger negative numbers, we're going to get smaller and smaller positive numbers that are closer and closer to 0. But we're never actually going to get a number that is less than 0 as our output. We're never going to get a negative output, right? So if we continue this trend to the left, we're going to notice that our function outputs, we could say, approach 0. Our outputs approach 0, right? We're getting incredibly tiny numbers here, but they're never actually going to reach 0. And so we can also, in addition, we can say that, that our function will never hit or go below the x-axis. And we have a word for this kind of behavior. If the outputs are approaching a specific value, we call this asymptotic behavior. And we could draw some imaginary line that this function appears to be approaching, right? This function appears to be approaching the x-axis. It appears to be approaching the line y equals 0 that I'm drawing in this dotted red line, but it's never actually going to reach it. And so more technically, we can say that an asymptote exists here. And this is an asymptote at y equals 0. An asymptote is some line that the graph of a function will approach, but never quite reach. Now, this kind of appearance for our graph, this kind of appearance is going to be true, actually, for absolutely every exponential function with a base that is larger than 1. So if we have a base of 3 or a base of 4, like if we have y equals 4 to the power of x, or y equals 9 to the power of x, or if we have y equals any base that is larger than 1, all to the power of x, this is what our graph will always look like. We will have this sort of asymptotic behavior at y equals 0, right? If we keep going to the left in our inputs, we will keep approaching 0 in our outputs. But if we keep going to the right with our inputs, then we will keep approaching larger and larger outputs, actually. So larger inputs mean incredibly large outputs, and smaller inputs and more negative inputs mean that we will be approaching 0. Is the function increasing or decreasing? So let's answer this question here. Really, this question is asking, as your inputs get larger, what happens to your outputs? Well, your outputs get smaller, right? Here, x represents our inputs, and f of x represents our outputs. As our inputs increase, what happens to our outputs? Actually, that was very silly of me. Clearly, as our inputs get larger, our outputs are getting larger. So I'll correct that mistake there. Here, as our inputs are getting larger, our outputs are actually getting much larger. So is this function increasing or decreasing? It's increasing. As our inputs increase, our outputs increase as well. So we call this exponential growth. And in our next video, we're going to look at an example of exponential decay.